Now we get to these instructions. On the graph of period versus length, which would be this graph, we want to give the coordinates of 2 points. Now, as I introduced in class, you don't want the 2 points to be close together, so you use 2 points that are pretty far apart. Okay, this is 0.55. Right here would be 0.275. We'll call that 0.28. And the coordinate of this point looks to be 1. So we're going to say, okay, we're going to use the coordinates 1.28 and let's see, this is 0.825 up here, and this is 1.1, so that's like about 0.3. So I'm going to say that 0.9 is going to be about here. There's 0.9 on the y-axis, and if we project 0.9 over here and straight down, it looks like we've got 4.2. Now, my estimate is not nearly accurate enough to justify 2 significant figures, but it's a little better than 1 significant figure, so I'm going to pretend that I was able to estimate that with that sort of accuracy, okay? So I've got 2 points. Now, people did this in class, as I say, following this step by step, and we kind of checked around, made sure people were on the right track, and people did quite well with it. But I'm going to go ahead and write some of these steps in. Okay, so first thing then, so we got the coordinates of 2 points. Plug the coordinates of the first point into the form y equals ax to the p. Now, you should do that before I write it down. First point, coordinates are 1.28. Okay, so what do you get if you plug those in? Hopefully you paused and wrote it out. We're going to get 0.28 equals a times 1 to the p. Now we plug the coordinates of the second point in, 0.9, 0.42. So we get what? I'll try to write it down here a little close to the bottom of the board, but 0.42 should equal a multiplied by 0.9 raised to the power p. Okay, so now we have 2 equations and 2 unknowns. Okay, so we want to solve those equations by elimination. And then we're going to get values for, well, what are our unknowns? A and P. Okay, so from the first equation, well, I lucked out. I got 1 for my P value. So this is just going to give me 1. And I'm going to get A equals 0.28. Then I can plug that value of A in here and obtain the value of P here. I'm going to have 0.28 times 0.9 to the P equals 0.42. Okay, well, I'm not going to write all that out, partly because I don't have room, and partly because people didn't really have any trouble with it. Another strategy for solving 2 equations like this, if I didn't have a really convenient number like 1, if I had a number like 0.77 or something, I could divide this equation by this one. If I divide the left-hand side by the left-hand side, I have 0.28 over 0.42, which turns out to be 2/3. That's kind of convenient, but it's not usually convenient at all. A times 1 to the p divided by a times 0.9 to the p. If I divide this by this, the a is divided by a, giving us 1, and then that's multiplied by whatever this is to the p divided by whatever this is to the p. Of course, one number to the p divided by another number to the p is the first number divided by the second number, all raised to the p power. At that point, I have an equation just like this. Some number to the p power equals whatever the left-hand side is here. In this case, it's 2/3. So we would have Some number raised to the p equals 2/3, and p would equal the log of 2/3 divided by the log of whatever this number is here. Having obtained the values of a and p, we plug them back in here. Most people got results that are pretty close one way or another to 0.4 times x to the 0.6 based on this graph. Or maybe this is based on the graphs that they had in front of them, so we can see if 0.4 times x to the 0.6 would be a good model for the data points that I observed. Raise 0.9 to the 0.6, that would be x to the 0.6, and then multiply that by 0.4. And that would actually come out fairly close to 0.42, but it'd be a little less than that. And then we could do the same thing here. And it wouldn't come out quite as close. It would come out with 0.4, where we should get 0.28. But that's how this would be done, and that is the procedure.